Welcome back to the Energy Conversion Lectures. In this lecture, I will review and explain two important and fundamental laws. These laws are Faraday's and Lenzs laws. In general, Faraday's law stated that the time-varying magnetic field linkage psi through the coil will induce a voltage across the coil. The voltage induced across the coil can be denoted by a small letter e and is equal to d psi over dt, and this will equal to d n phi over dt. As you can see, this relationship, or Faraday's law, represents the interaction between the electrical energy, represented by the induced voltage E, and the magnetic field energy, represented by magnetic field linkage psi, or the magnetic field lines phi. Identifying the polarity or direction of the induced voltage across the coil of the magnetic circuit is different from identifying the voltage across a resistance. The voltage polarity across a resistance R is always opposite to the direction of the electrical current flowing through the resistance. However, the voltage induced across the coil is depending on the electrical current direction and the winding direction of the coil. The polarity or direction of the induced voltage E of the coil can be identified by using Lenzs law. Lenzs law stated that the polarity of the induced voltage E is such as to circulate a current, of course if the circuit is closed, to oppose the change of the magnetic field linkage. To explain these two laws in details, first we need to understand the difference between constant and time-varying magnetic field concepts. Let's assume we have an electromagnet supplied by a DC source through a resistance R. The DC source has constant voltage value E with respect to time, and therefore a constant current I will flow through the coil of the electromagnet. Based on this configuration, a constant magnetic field lines phi will be produced in one direction. That means the magnetic field lines that are linked to the coil turns psi are constant as well. This will lead us to the conclusion that the induced voltage across the coil will be zero when the magnetic field is constant or not time varying. In other words, the derivative of constant value of magnetic field linkage psi will be zero. Based on this conclusion, the voltage E will be equal to I times R. Now let's apply a sinusoidal AC source to an electromagnet through a resistance R. The AC source has a time-varying sinusoidal voltage V, and therefore a sinusoidal current I will flow through the coil of the electromagnet. Based on this configuration, a sinusoidal or time-varying magnetic field lines phi will be produced. It is very clear that the magnitude and polarity of the magnetic field is changing with the time. So within one cycle, the magnetic field can be positive increasing, positive decreasing, negative increasing, and negative decreasing. Therefore, an induced voltage E will be generated across the coil according to Faraday's law, and the induced voltage E will be equal to d psi over dt, and this will equal to d n phi by dt. As mentioned earlier, the polarity of the induced voltage can be identified using Lenzs law. To understand how to determine the polarity or direction of the induced voltage using Lenzs law, let's apply some steps to the following electromagnets and try to cover all the possible cases. The first step is to hypothetically close the coil circuit through a resistance. Now, based on the main current I, determine the polarity of the magnetic field lines phi using right-hand rule. After that, identify the direction of magnetic field change delta phi. In other words, identify if the magnetic field is increasing or decreasing. Note here that the magnitude of delta phi is smaller than the main magnetic field phi. The fourth step is to draw magnetic field phi O in opposite direction to the direction of magnetic field change delta phi. The fifth step is using the right-hand rule to identify the direction of the current IO that should flow to generate the magnetic field phi O. The sixth and last step is to set positive sign at the place where the current IO is out of the coil and negative sign at the place where the current IO enters the coil. As you can see, after all these steps, the polarity or direction of the induced voltage have been identified. I need to mention here again that when an AC source is applied to a magnetic circuit, the voltage, current, and magnetic field are changing in magnitude and polarity with the time. In other words, these voltage, current, and magnetic field are time-varying variables. It should be noted here that even if the AC source alternate between positive and negative cycles, there should be some polarity or direction assigned to the voltage source and the current flowing to help in solving the AC electric and magnetic circuits. Let's have the following example with the following assigned polarity and direction to the AC voltage and AC current. Based on Faraday's law, since the magnetic field is time varying and not constant, an induced voltage E will be produced across the coil of the magnetic circuit. Based on the assigned voltage and current directions, the polarity of the magnetic field phi can be determined based on the right-hand rule. To identify the polarity of the induced voltage E, Lenz's law will be applied as follows. Let's assume that the magnetic field phi is increasing by delta phi in the direction shown. To identify the polarity based on Lenz's law, first we need to close the circuit of the coil. In this example, the circuit is already closed through the AC source and the resistance R. Then we need to find the magnetic field that opposes delta phi. The magnetic field that opposes the delta phi is denoted by phi O. Now we can identify the current direction that opposes phi O based on the right-hand rule, and it is denoted by IO. Based on this direction of the current IO, the polarity of the induced voltage will be positive sign at the place where the current IO is out of the coil, and negative sign at the place where the current IO enters the coil. Therefore, the voltage equation of this magnetic circuit can be written as follows. V equal to IR plus E, and this will be equal to VIR plus N d phi by dt. Note that the positive sign is identified based on the polarity or the direction of the induced voltage. Now let's apply Lenzs law to the following magnetic circuit to identify the polarity of the induced voltage across the coil A and coil B. First, let's start with coil A. Based on the assigned voltage and current polarities and directions, the polarity of the magnetic field phi A can be determined based on the right-hand rule. Let's assume that the magnetic field phi A is increasing by delta phi A in the direction shown. After that, we need to close the circuit of coil A using a resistance. Actually, coil A is already forming a closed circuit with the resistance R1 and the AC source. Then we need to find the magnetic field that opposes delta phi A. The magnetic field that opposes delta phi A is denoted by phi OA. The current direction that produces phi OA can be identified based on the right-hand rule, and it is denoted by IOA. Based on the direction of this current, the polarity of the induced voltage will be positive sign at the place where the current IOA is out of the coil, and negative sign at the place where the current IOA enters the coil. Let's apply same concept and procedure to coil B. First, we need to close the circuit using resistance R2. Then, we need to identify the direction of the actual magnetic field that links to coil B. In this case, the actual magnetic field that links to coil B is generated by coil A and is denoted by phi B. Basically, in this example, phi A equals phi B. Assume the magnetic field is increasing by delta phi B in the direction shown. The magnetic field that opposes delta phi B is denoted by phi OB. Therefore, the current direction that produces phi OB can be identified based on the right-hand rule, and it is denoted by IOB. Based on the direction of the current IOB, the polarity of the induced voltage will be positive sign at the place where the current IOB is out of the coil, and negative sign at the place where the current IOB enters the coil. Let's conclude this lecture at this point, and we'll continue in the next lecture. Feel free to leave comments and suggestions. I am Ihsan Al-Nabi, and it was a pleasure sharing this lecture with you. Thank you.